Mm, mm, mm. Sí, ¿por qué no se enciende mi cámara? Oops. Hello, guys. Good evening, everyone. Thank you for coming on time. I'd like to say hi to the ones I see here. I'd like to say hi to Karen, to Melanie, to Stephanie, to Orlando, to Jenny, to Sebastian, to Juan Sebastian, to Gabriela, and to Caroline. Thank you for coming, guys, on time. Uh, please remember we have homework and assignment due this Friday. If you notice, there was a modification on the assignment number 3, just to make it on problem number 2 is in a way similar, not exactly, but very similar to the problem that you guys had in the midterm exam. So I'd like to show you guys that, so at least you are aware. So this is assignment number 3. We can minimize ourselves. And you will see that in problem number 2, this was changed because the previous problem was taken from another book, from Gavin Towler's book. And I had the suspicion that that particular problem, it was an absorption problem. There was some chemical reaction taking place. And we wanted to be consistent with the fact that we have addressed this topic of absorption, desorption, and even evaporation only from the physical standpoint, and leaving a more complex type of interactions, separations for the simulation software. So what we did is we took a problem from the University of Colorado that was presented. I mean, this is publicly available, so it's not like I took any secret information. It's available for the public, and I just did a small modification to it. In a way, it looks similar. Actually, the problem that you guys had for the midterm exam was a bit simpler because in the midterm exam, I gave you the concentration, the target concentration in the liquid. So it is very similar. You might recognize many of the numbers in here, very similar, except for the fact that in this case, you are not given the target concentration of CO2 in the liquid stream. You guys will need to use the Henry's law to determine what will be the target concentration based on the equilibrium that Henry's law is going to give you. And then you will determine that for yourselves. So that's the only difference, guys. Okay. It's not that difficult. It just takes a bit more time. Okay. Let's check our syllabus, guys. Thank you for coming, everyone, the ones that just joined us. Hope that you all guys are doing well. Let's go for the syllabus for our class. If we can find that somewhere in here. Where is our syllabus? Let's try to find our syllabus. Okay. So for tonight, we need to continue on our discussions of process heat recovery. There is an assignment this Friday, and hopefully wrap up this discussion and finish on December the 5th. To begin our discussion with chemical reactors and then followed by the economics of plant design. Hopefully by then we can confirm the workshop with Dr. Varela. And then the location of chemical plant. These are, the last topics, the remaining topics, which are like complementary topics. The location of a chemical plant, the layout of a chemical plant, the environment, its environmental impact on the community surrounding the plant, and accidents and troubleshooting in chemical plants. So they're the very last like complementary topics. So you will see that the class mostly makes emphasis in process. We do a review on different process topics like pumps, like heat exchangers, like separations. Right now, heat recovery, and then we move on hopefully to reactors before we go on on the economics of the plan, and then just three complementary topics. You will find these videos. They are recorded as with the title of process heat recovery. Let me see if I can find that. So we have our videos in the same place where all the videos are for this class. They are unedited, so whatever we say is just recorded there. Let me just share with you guys where the videos are. Okay, so this is the page where our videos are in the cloud. So you guys, many of you have already seen many of these. This set of discussions, let's see, is going to be stored as process heat recovery. You will find that on the 2.2 process heat recovery. That's the first class we had on Tuesday. So hopefully today there will be another video called process heat recovery 2. And if we have a new class on next Tuesday, that will be process heat recovery 3. So it will be under 2.2 because this is an extension of the discussion of heat exchangers, but now focusing on the recovery of heat. So it's going to be called process heat recovery. In case you guys want to later on take a look at the videos. Okay, just let's move on for what we have for today for our class. We can find our slides. So these are our slides, and our very last time, or towards the end, let's just say towards the end of our class, we discussed the topic of the problem table algorithm. See, this is the problem table algorithm. Okay. So let's hope this bar moves so we can put this on presentation mode. See if we can use this. It says a problem table algorithm. And the bar is still there. Let's see. Okay. Where is this? There we go. So, vamos a mantener esto hasta que se suba la barra, y una vez que se suba la barra ya podemos trabajar con esto. Cuando iniciamos aquí. So the problem table algorithm, we discussed that there is a way of having these, let's just say the composite, the hot composite curve and the cold composite curve, they could be expressed numerically in a table without having to draw the plots, you know, the composite curve, the hot and cold composite curves. And that is called the problem table, I'm sorry, problem table algorithm. It's like an alternative to do that. And we showed that there were steps to do that. The first step, let's see if we can find number 1. For some reason, I don't find number 1. Maybe there. Set up shifted temperature intervals from the stream supply and target temperatures by subtracting delta T minimum divided by 2 from the hot streams. There you go. Maybe we can have presentation mode. Okay. Set up shifted temperature intervals from the stream supply and target temperatures by subtracting delta T minimum divided by 2 from the hot streams and adding delta T minimum divided by 2 to the cold stream, as in figure 1614. What is that figure? This is 1614. Okay. We also explained, you know, these dashed lines were delta T minimum divided by 2 minus the hot composite curve. And this dashed line here was delta T minimum divided by 2 plus the values of the cold composite curve. So eventually they do touch in there, right there, where the pinch point is. Okay, so that would be number 1. Number 2, we have to do an energy balance. So that would be the summation of MCP. It is represented by just big CP of the cold stream, CPC, minus summation of the big CP, MCP. This is what it means, MCP, of the hot stream. So summation of the cold streams, of the big CPs of the cold streams, minus the big CPs of the hot streams, times delta T of a specific interval, delta T sub I of a specific interval. Okay, so we went over this last time, explained this in a bit more detail. And there was this exercise. There was a simple exercise, and they were moving on to another exercise about this, where we could see that on figure 16.2, we have 4 streams, these 4 streams, 2 cold streams where the temperature was increased, and 2 hot streams where the temperature was reduced. To work this type of algorithm or this type of tables, we needed to do that calculation for the shifting. That is, when the stream was cold, then we will take delta T minimum divided by 2 plus the supply temperature, which was 25, and the target temperature, in this case, was 180. So 25 plus delta T minimum, which is what was delta T, 10 divided by 2 is 5. So that will be 5 times 5 plus 20 is 25, and 5 plus 180, 185. So that will be the protocol or the procedure for cold streams. For hot streams, it will be the opposite. That you have 250 minus delta T minimum divided by 2, so that will make 245 for the supply, and also the same will be for the target temperature, 2, that will be 35. So you repeat that for the hot streams, where you subtract delta T minimum divided by 2 from the supply and target temperatures, and then you add on the cold streams delta T minimum divided by 2, both on the supply and target temperatures. That's why you end up with these shifted temperature intervals on the right, in these 2 columns on the right. Based on this, then you do your scale. Remember, this scale is not a well, let's just say, scale. It obeys no scale. There is no scaling here, because you will see this starts from 25. It goes, an interval of 10 degrees Celsius, and then it jumps in an interval of 40, and then it jumps in an interval of, what is this? About 70, and then another 40, and then 10, and then 40, and then 10 again. So this obeys no scale whatsoever. So what we're doing is just taking the interval is going to be made out of these temperatures in order from the lowest, or if you come from the top, it will be the highest to the lowest. That will be perhaps easier. Or you go from the lowest to the highest, whichever is easier for you. If you go from the lowest to the highest, it will be 25 at the very low end, then 35, then 75, then what else we will have? I guess we'll have 145, then 185, then 195, then 235, and 245. And that should be reflected exactly in here. Then 25, 35, 75, 145, 185, 195, 235, and 245. And then on this scale with the dashed lines, every dashed line separates the temperature interval. There's a temperature interval in this region. There is another temperature interval in this region, and another one in this region, and another one here, another one here, another one here, and the final one here. You use these dashed lines to place the starting point and the end point of every one of these shifted temperatures streams. So say for example, for the cold stream starts now at 25. This is the shifted temperatures of the cold stream, not the actual temperatures, because these are the actual temperatures. So on the shifted temperature scale, it should start from 25 and go all the way to 185. And that's what you see there. It starts from 25 and goes all the way to 185. And on the right, the author included the actual temperatures. That you wouldn't need to do that, but for illustration purposes, it just refers to that this actually is referring to, or is representing an actual temperature of 20, since this is being heated. On the second one, which is stream number 2, which is a hot stream, the shifted temperatures tells us that it's going from 245 to 35. So that will be 245 all the way to 35 on the shifted temperature scale, although the actual temperature will actually be 250 all the way to 40. And we'll repeat the same for the other 2 streams. Also make mention that then we needed to do the energy balance, and then we mentioned how to do the energy balance when we had the different delta T's from the different intervals, and we need to take into consideration the summation of cold CPs minus hot CPs within that interval. So for that, let's say this specific interval, we have no cold CPs, we only have one hot CP, which will be 0 minus the summation of the cold, which is just 1 in this case, minus 0.15. So times 10, that will be minus 1.5 megawatts. It was a surplus because it has a negative sign, it's giving out heat. And in the second case, it was the result was a positive result. It was needing to have this amount of heat as input, 6 megawatts. And this came as there was a 40 degrees Celsius temperature difference in this interval. The summation of the cold CPs, that will be cold because it was coming from a low temperature to a higher temperature. So within this interval, we only have one cold CP, which is 0.3, and one hot CP, which is 0.15. So 0.3 minus 0.15 is 0.15 positive times 40. That's what you see there, 6.0 megawatts. So we repeated this for the rest, and that's why you will see some of them will have a negative sign. There was a surplus energy, and some of them there was a positive sign. There was a requirement of energy. So then we moved on for the table algorithm, the problem table cascade, which is very interesting because at the end of the day, if you recognize these different delta H's, they all come from the table. That is, they all come from this table. So if you did a good job on the energy balance within every interval, if you did a good job, then you can use the delta H's of every interval exactly and place them on top of each other on this table algorithm, on this table, on the cascade table. So you start the first one, which is a hot utility coming in, and the intervals, these intervals are the exact same intervals as the ones you will see here, which are the same intervals as the one we saw here. These are exact same intervals. They all came from the table. They all came from the table. These are all shifted temperatures that were used for the stream population data graph, stream population data, however you want to call it, graph or something. And then they were used for this table, for the heat balance table, the same temperature intervals. And then you move on. So on the cascade diagram, you use the exact same temperature intervals. So within the intervals, just like you see here, say, within 245 and 235, you have minus 1.5 megawatts. Within 235 and 195, you have 6.0 megawatts. Within 195 and 185, you have minus 1.0 megawatts, and so on and so forth. So that should reflect what you see on this cascade table. You have within 245 and 235, you have minus 1.5 megawatts. Between 235 and 195, you have 6 megawatts. Between these two, within this temperature interval, between these two temperatures, you have minus 1.0 megawatts, and so on and so forth. You see that both tables have exact same temperature intervals, and they have the exact same heat balance. They say in the form delta H, expressed as delta H, which is Q, it's just heat balance. So delta H is within these intervals minus 1.5 megawatts, which is the same in here, and so is 6, and so is minus 1, and so is 4, and so is minus 14, and so is 2, and so is 2.0. So they're exact same energy balance for the exact within the exact same intervals. So far so good. So these two tables, they look almost exactly the same, except for the fact that on the table on the left, you actually have an input of hot utility. You have a withdrawal of cold utility. You see the same on the right, but you start on the at the very top. You start with 0 megawatts. On the cascade, let's say cascade table on the left, you start with 0 megawatts. You start subtracting 0 minus 1.5 is plus 1.5. So plus 1.5 minus 6 is minus 4.5, minus 4.5 plus 1 is minus 1 is plus 1 is minus 3.5. Minus 3.5 minus 4 is minus 7.5, minus 7.5 plus 14 is 6.5. 6.5 minus 2 is 4.5. 4.5 minus 2 is 2.5. There's a mistake in here. It's not 0.25, it's 2.5. So we mentioned that we have to be very careful in observing. First, on the table on the left, you always start with 0 megawatt at the very top. So you start simulating there as if there were no heat supply. That's what you see there. I'm sorry. That's what you see there, no heat supply. So you start as if there were 0 megawatts. And then you start, doing the cascading down all the way to the bottom. And then you select the largest negative heat flow, the largest negative flow. The largest negative heat flow will represent, right there, will represent the input, the QH input as your hot utility. Why is it? So it means it could be this amount or a larger amount, but at least this amount. Since we're focusing on a QH minimum, the minimum amount of energy required by your process, remember that the more energy that you input in a process as live steam, I make emphasis of live steam, vapor vivo, se le dice aquí comúnmente en la industria ecuatoriana, vapor vivo. ¿Por qué es vivo? Bueno, es un vapor que requiere un combustible, la quema de un combustible. Creo que he expresado anteriormente ese combustible. Generalmente es bunker, es fuel oil 6, bunker. Bunker C es técnicamente el nombre. Pero es un combustible pesado. Está hecho de una mezcla de hidrocarburos largos, de cadena larga. Al quemarlo produce material particular. Bueno, es un verdadero desastre, ¿no? Y desastre desde el punto de vista ecológico, porque va a emanar material particulado. Si usted se para detrás de una metrovía cuando arranca, creo que es una imagen común que tiene, cómo sale una nube negra, ¿no? Detrás de la metrovía. Y tiene un motor diésel enorme, ¿no? Esa nube negra tiene bastante concentración, una concentración considerable, muy probablemente, de material particulado, PM2.5. Trate en lo posible evitar a toda costa respirar eso, eso es cancerígeno. Trate a toda costa evitar respirar ese tipo de, respirar en ese tipo de ambiente. Póngase un pañuelo si le es posible, ¿no? En fin, estábamos aquí. The largest, so we have the largest negative magnitude here on the cascade table on the left. That will represent the positive, you see, shifting from negative to positive. Your positive input in the form of live steam into the cascade on the right. So now you're taking the same magnitude that will represent QH minimum, the minimum amount of energy in the form of live steam. Why is it in the form of steam? Steam is the cheapest way, let's say the cheapest utility you can use to heat up different process vessels or to heat up different process streams. It is the cheapest way to do that, to use steam. Because if you remember, 1 bar is approximately what, 22 or 2700 kilojoules per 1 kilogram of saturated steam. So it's when it condenses, when saturated steam condenses, it gives up more than what, 2,000 kilojoules of energy. So it is a lot of energy per kilogram of saturated steam. That's why it's way cheaper to use steam than any other way of heating up a process. Another way to do that, of course, is just by burning fuel. Then you burn fuel and then you have an indirect heating of some organic fluid going into pipes, into tubes. It's another way to do that. But that is another topic of discussion. I think later on in these slides, we'll see an example of a comparison between two different ways of heat, doing the achieving heating in a process, in a given process. So we use a 7.5 as QH minimum, and then we do the cascade down, and eventually find the pinch point, as we see right there. And by the very bottom, we find the QC minimum, which by now is 10. So if you remember at the very beginning, we saw we had these hot composite curves with delta T minimum of 10 and cold composite curves with delta T minimum we had an example of delta T minimum of 10 and an example of delta T minimum of 20. On the one that had a delta T minimum of 10, and we needed to supply 7.5 megawatts to the right of the diagram, if you guys remember. And we needed to withdraw 10 megawatts on the left side of the diagram. So these represent the exact same numbers, but now on the table, which is easier to read. So these comments, they are comments regarding what we saw in these tables. It says the first interval has a surplus of 1.5 megawatts, which is cascaded to the next interval. That's why you say this 1.5 megawatts is cascading all the way down, which leaves the heat from this interval to be minus 4.5, which you see right there. The third interval, the process has a surplus of 1 megawatt, which leaves minus 3.5 megawatts to be cascaded to the next interval. So this minus 1 megawatt, minus makes a plus, so this leaves a minus 3.5, and so on and so forth. These are just comments on those tables. To make the cascade feasible, sufficient heat must be added from the hot utility to make the heat flow to be at least zero. The smallest amount of heat needed from the hot utility is the largest negative heat flow from figure 1618A, that is 7.5 megawatts. So the largest negative heat flow that should be placed in here as QH minimum, just like we see right there. In figure 1618B, 7.5 megawatts is added from the hot utility to the first interval. This does not change the heat balance within each interval, but increases all of the heat flows between intervals by 7.5, giving one heat flow of 0 at an interval temperature of 145. So if we start with the magnitude of the largest negative heat flow in the cascade diagram on the right, we eventually will reach a 0 point, which is our pinch point. And that is where we see that the hot pinch is 145 plus delta T minimum divided by 2. And the cold pinch will be 145 minus delta T minimum divided by 2. And we'll end up with this delta T range of 104, which is a delta T minimum, 150 minus 140, this is 10 degrees Celsius, which was specified in the problem. Very well. Those the actual hot and cold extreme pinch temperatures are 150 and 140 respectively. Again, this agrees with the result from the composite curves in figure 16.5. The initial setting for the cascade, the heat cascade in figure 1618 corresponds to the setting for the shifted composite curves in figure 1615. The setting of the heat cascade for 0 or positive heat flows in figure 1618b corresponds to the shifted composite curve in figure 1615. So figure 1615 is what the cold and the hot composite curves. That is a graphic way of representing what we see in the table. And figure 1618 is a table cascade that we just saw. Composite curves are useful in providing conceptual understanding of the process, but the problem table algorithm is a more convenient calculation tool. Okay, so there is an example of this as a flow sheet for a low temperature distillation process is shown in figure 1619. This is another process, different than the one we saw in figure 16.2. Calculate the minimum hot and cold utility requirements and the location of the pinch, assuming delta T minimum is 5. So here we see all these streams, 7 streams. And we see the first one is going from 20 to 0. The second one is going from 19 to minus 20. The third one is going from minus 39 to minus 40. The fourth one is going from 19 to 20. The fifth one is going from minus 1 to 0. And the sixth one is going from 0 to 20. Okay. Some of these seem to be just condensing, like in this one, condensing. This one seems to be what? Boiling from 19 to 20. This one also seems to be boiling. But in any case, we have a group of hot streams and cold streams. So that is represented in this table. Okay. Where this CP is just obtained from, we know that MCP delta T is equal to Q. So if we solve for MCP, then we have Q divided by delta T. Q or delta H, which is Q, is energy. divided by delta T. And so we have minus 0.8 divided by the difference is 20. That's why you see the 0.04. And likewise, minus 1.2 divided by the difference in here, which is minus 1, is 1.2 positive. 0.8 divided by the difference, which is minus 1, is 0.8. Next one is 1.2 divided by the difference in temperature, which is 1 degree Celsius, which is 1.2. 0.8 divided by the difference in temperature, which is 1, is 0.8. 0.2 divided by the difference in temperature, which is 20, now 0.01. And the last one, 0.6 divided by the difference in temperature, which is enormous, is 60, minus 40 in the negative region and 20 in the positive region, so it's 60 degrees difference, 0.01. Very good. Now, we have 7 streams, as you guys might remember. These in this PFD, this process flow diagram, we see 7 streams. First one, second, third, fourth, fifth, sixth, and seventh. So we have 7 streams. So the conditions on every one of these has to be described on a table to make it simple to do calculations on. So that is going to be expressed. Well, it is expressed in here, and is again expressed in here. The reason why we have these 2 tables, the first one is to make sure we need, the necessary calculations, the energy calculations, the CP calculations, etc. Then here we have the actual temperature, supply and target temperature. Now what we're going to do is determine the shifted temperatures. Remember, for the hot stream, it's delta T minimum divided by 2. Now in this problem, as it says in this problem, delta T minimum was 5 degrees Celsius. So delta T minimum divided by 2 now is going to be 2.5 degrees Celsius minus the supply and target temperatures of the hot streams plus the supply and target temperature of the cold streams. So that's where you see an order listing of the hot and the cold streams. So for the hot ones, it's going to be the actual temperatures minus delta T minimum divided by 2. So it's going to be 20 minus 2.5 and 0 minus 2.5. Minus 19 minus 2.5 and minus 20 minus 2.5, and then so on and so forth. For the cold stream, it's going to be delta T minimum divided by 2 plus the supply and target temperature. It's going to be 21.5 and 22.5 and so on so forth for the rest. So thankfully, we have now our supply and target temperatures on the shifted scale. As you see there, this is on the shifted scale. This is the actual temperature. These are the shifted temperatures. And now we're going to do a population diagram. So here, these intervals, they come exactly from here. And if we track them down, the lowest one will be minus 42.5, minus 41.5. Next will be minus 37.5. I'm sorry. Yeah, minus 37.5. Then the next one would be probably what? 1.5? Maybe minus 2.5, sorry, minus 2.5, then 1.5, 2.5, then from 2.5, 17.5, then from 17.5, 22.5. So it's 21.5 and then 22.5. A bit confusing, but you have to do that carefully. So this shifted temperature interval has to reflect exactly that, coming from minus 42.5, minus 41.5, minus 37.5, minus 22.5, minus 21.5, minus 2.5, 1.5, 2.5, 17.2, I'm sorry, 17.5, 21.5, 22.5. So these are the exact reflection of these shifted temperatures that came from the actual temperatures of the PFD that we were studying. Then we have this stream population. Just to check, the first one is coming from 17.5 to minus 2.5, stream number 1, so from 17.5 to minus 2.5. And then we include the CP. So the CP was calculated on the previous table. CP for stream number 1 is 0.04. So that's why you see the 0.04. And we have to repeat the process and do that for every one of the streams. So we complete our stream population. within the interval, the shifted temperature interval, then we know that we have to calculate the delta T for every interval. This case is 1 degree, in this case is 4 degrees, in this case is 15 degrees, and so on forth. Just the temperature difference within each interval. Then the summation of cold CPs minus hot CPs. So within every interval, in this case, we have 1 cold, 2 cold, 3 colds, and no hots. So it will be 0.01 plus 0.01 plus 1.2. So it's 1.22 times delta T is 1, so that will give us 1.22. So it's positive, so it's a deficit in energy. We do the same for the rest. String number 1, etc. Finally, the cascade is shown in figure 1621. Figure 1621A shows a cascade with 0 hot utility. This leads to a negative heat flow, with the largest one being minus 1.84. Adding 1.84 megawatts from the hot utility as shown in figure 1621B, I think it's referring to this, 1621A and 1621B, gives QH minimum of 1.84. So let's check on that. So these obeys all these temperature intervals from minus 42.5 to 22.5. They obey these exact temperature intervals. And the delta H's that you see, the heat balance, they are this magnitude, this value, these exact values within every temperature interval is going to be expressed on the cascade table. And that's what you see on the first, within the first interval, we have delta H of 1.22, which came from here. Within the second interval, we see a delta H of 0.08. Within the third interval, we see a delta H of minus 0.3. And that's why you see 1.22, 0.08, minus 0.3. So both values on the left cascade table and on the right cascade table, they're exactly the same. The difference is that on the cascade table on the left, just like you see here, we start with a 0, and we start cascading down until all the way to the bottom. So 0 megawatts of input in energy on this process, minus 1.2 is minus 1.22, minus 1.22, minus 0.8 is minus 1.3, minus 1.3 plus 0.3 is minus 1, minus 1, minus 0.77, minus 1.77, minus 1.77 plus 0.12 is minus 165, minus 165, minus 0.19 is minus 184, minus 184, plus 119 is minus 0.65, minus 0.65, minus 0.15 is minus 0.8, minus 0.8, that would be plus 0 is minus 0.8, minus 0.8, plus 0.8 is just 0. Okay, so the largest with negative heat flow belongs to minus 184, which is used as a positive input on the cascade table on the right. So that's why you see 184 on the top. And once again, you start cascading down this, and you see doing all this subtraction until you find where you have a 0, and that 0 corresponds to the pinch point. So that means if the pinch point is minus 1.5, minus 21.5 on the shifted temperature scale, and you had a delta T minimum of 5, that means that the hot pinch is going to be this value plus 2.5, and the cold pinch is going to be this value minus 2.5. So you have a 5-degree difference between minus 19 and minus 24. So the hot pinch is minus 19 and the cold pinch is minus 24. Also, you already found QH minimum, which is 184 right there. And when you did this heat balance cascading the heat all the way down, you also found QC minimum, which is 184. So far so good. You have found QH minimum, QC minimum, the hot pinch, and the cold pinch. So far so good. Now, we hopefully finish our discussion on the utility selection, which is an interesting topic too. It means after maximizing heat recovery in the heat exchanger network, those heating and cooling duties not serviced by heat recovery must be provided by external utilities, just like we said. using steam to supply the QH minimum, using cooling water to withdraw, waste heat in a given process. The most common hot utility is steam. It is usually available at several levels. High temperature heating duties require furnace, flue gas, or a hot oil circuit. Y hay casos especiales que requieren temperatura superior a la que pueda suplir el vapor saturado, porque el vapor saturado hay una relación directa con la presión, ¿no? Y un equipo a muy alta presión no deja de ser un equipo peligroso también, además de ser muy caro, ¿no? Entonces también se lo puede suplir si es un requerimiento de temperatura muy alta en un circuito de aceite caliente, dependiendo del requerimiento del proceso. Cold utilities might be refrigeration, cooling water, air cooling, furnace air preheating, boiler feed water preheating, or even steam generation, if heat needs to be rejected at high temperatures. Although the composite curves can be used to set energy targets, they are not suitable tool for the selection of utilities. Quiere decir que las curvas compuestas, calientes y frías, a pesar de que nos ayudan a determinar el QH mínimo y el QC mínimo y la cantidad de calor que puede ser regenerado, que puede ser caer en cascada de las líneas calientes compuestas a las líneas frías compuestas. Esa información es valiosa, pero no nos ayuda a determinarla o emitir un juicio de valor en cuál sería cuál sería el servicio utilitario para proveer el calor a la planta más adecuado. Esto no nos dan las curvas. Para esto nos recomiendan el Grand Composite Curve. The Grand Composite Curve is a more appropriate tool for understanding the interface between process and the utility system. Y esto el autor, que es Smith, toma mucho cuidado en citar a todas estas diferentes fuentes, entre las cuales está el señor Linhoff, con su equipo de trabajo, Ito, y el señor Townsend con el señor Linhoff. Tiene publicaciones en diferentes años, aquí según observo en los años 80, al principio de los 80. The Grand Composite Curve is obtained by plotting the problem table cascade. A typical Grand Composite Curve is shown in figure 1624. Vamos a ver, esta tabla se obtiene graficando las temperaturas modificadas, las temperaturas de intervalo modificadas, no las actuales, no son las verdaderas, sino las modificadas, ¿no? Con el delta T mínimo dividido para 2, más la temperatura provista y la temperatura final, ¿no? De la línea caliente y de la línea fría. Bueno, esas temperaturas modificadas se grafican contra el delta H. Se obtuvo esta información del diagrama de cascada. Las temperaturas vinieron de aquí y los delta H vinieron de acá. Entonces, en los delta H del menor al mayor se hace por una escala. Y de las temperaturas, pues obviamente se obtiene una escala. Claro que en el diagrama, pues estaría ya un espaciado más homologado, ¿no? Porque es un gráfico en sí. Obtendríamos algo así. Y este gráfico se explica, lamentablemente puse la explicación antes del gráfico, pero bueno, nos dice así. The Grand Composite Curve is obtained by plotting the table cascade. It shows a heat flow through the process against temperature. It should be noted that the temperature plotted here is shifted temperature and not actual temperature. Hot streams are represented by delta T minimum divided by 2 colder, and cold streams by delta T minimum divided by 2 hotter than they are in practice. Thus, allowance for delta T minimum is built into the construction. The point of zero heat flow is a Grand Composite curve. In the Grand Composite curve is a heat recovery pinch. The open jaws at the top and at the bottom are QH minimum and QC minimum respectively. Vamos a observar esto. Thus, a heat sink above the pinch and the heat source below the pinch can be identified as shown in figure 1624. The shaded areas, las áreas en gris, known as pockets, represent areas of additional process-to-process heat transfer. Remember that the profile of the Grand Composite curve represents residual heating and cooling demands after recovering heat within the shifted temperature intervals in the problem table algorithm. In the pockets in figure 1624, a local surplus of heat In the process is used a temperature difference in excess of delta H to satisfy the local deficit. It reflects a cascading of excess heat from high temperature intervals to low temperature intervals in the problem table algorithm. Entonces vemos aquí que esta parte abierta representa justamente donde se va a ingresar, donde en el proceso se va a ingresar calor en la forma de vapor. Aquí lo ingresamos el mínimo requerimiento de vapor, QH mínimo, es el Hot Utility Likely Steam. Y en esta parte abierta del fondo es donde el calor es rechazado, probablemente va a ser absorbido, como decíamos, por el agua de torre. Y representa el QC mínimo, la mínima cantidad de energía que va a tener que ser absorbida por un servicio utilitario como el agua de torre. Este punto de aquí representa el punto pinch. Sobre el punto pinch, el proceso actúa como un absorbedor de calor, heat sink, y debajo del punto pinch, el proceso es absorbedor de calor porque está absorbiendo el calor de QH mínimo. Y debajo del pinch está comportándose como un proveedor de calor, heat source, porque está está proveyendo esta energía que es energía de desperdicio, energía en exceso, que le está enviando al ambiente o la va a tener que absorber el agua de torre. Entonces actúa como source of heat, como heat source. Aquí hay, pues, se dice bolsillos de energía recuperada, heat recovery, de bolsillos de energía que se pueden utilizar para interacción de proceso a proceso. Y el punto pinch. Figure 1625A shows the same grand composite curve with the two levels of steam used as hot utility. Figure 1625B shows again the same grand composite curve with hot utility, hot oil used as hot utility. Entonces vemos en el de la izquierda, una vez más vemos la gran curva compuesta, vendría a traducirse grand composite curve, la gran curva compuesta que es el gráfico de las temperaturas modificadas contra el delta H de diagrama de cascada, ¿no? Aquí se puede observar dos procesos de calentamiento. Típicamente acá localmente se usa es vapor saturado, como he mencionado varias veces. Dependiendo del proceso se usan 120, 150 psi de presión a la salida del caldero, pero hay procesos como para el café soluble instantáneo que se requieren presiones de 230 o algo así, PSI, ¿no? O sea, es un vapor de alta presión. Pues tendríamos, en el proceso que usa caldero, tendríamos un caldero de alta presión, tendríamos una línea de alta presión y según se observa aquí en este pequeño PFD es una línea de baja presión. Aunque en la vida real el caldero solo tiene de salida una línea, sea de alta o de baja presión, no tiene dos líneas. Lo que sí ocurre es que la línea, digamos, de alta presión del caldero va a un distribuidor, el distribuidor luego va a un reductor de presión y se baja la presión justamente para el servicio de calentamiento que no requiere tanta temperatura. Recuerda que hay una relación directa presión-temperatura. Entonces, usted requiere tanta temperatura, le baja la presión a la línea con un reductor de presión y envía la línea de vapor con la presión reducida al servicio que requiere. Básicamente así es como se hace en la vida real, ¿no? Pero bueno, volviendo al PFD, estas dos líneas generalmente entregan calor y usted ve cómo entregan calor al proceso en esta simbología que se encuentra aquí y retorna el condensado, como puede observarse. Estas dos líneas representan la línea de vapor de baja presión, su temperatura, porque es su temperatura modificada en este eje de la Y, es la temperatura, y la línea de la temperatura que representa la línea de alta presión. Vemos también el intervalo de baja presión y el intervalo de alta presión. Es decir, en este proceso se siguió dos pasos. Yo tiendo a pensar que se usaron dos calderos, un caldero de baja presión y un caldero de alta presión, para lograr el objetivo finalmente llegar a esta temperatura, es lo que tiendo a pensar. En el diagrama de la derecha se usó solamente aceite caliente y como fue aceite se lo calentó hasta este punto, una sola línea como usted puede ver. El aceite es calentado, esto es un fuel furnace, aquí se quema combustible, se calienta indirectamente el aceite, va al proceso, entrega calor que requiere en el proceso y luego, una vez que entrega calor, es bombeado de regreso en el circuito de calentamiento al horno. Esto es un horno, furnace. Okay. Aceite caliente, ups, y el retorno. Temperatura del aceite caliente y acá está el punto pitch. Recuerde que así como en el caso del vapor de alta presión, una vez que entrega el calor, finalmente, si, al actuar como fuente de calor, el QH mínimo entrega el calor, el proceso absorbe el calor y ese diferencial de temperatura es la fuerza motriz, digamos así, del proceso en su requerimiento. Hasta que entrega el calor, finalmente se ha entregado y llega usted al punto pinch en la parte del proceso que absorbe calor. Lo mismo ocurre si se utiliza otro combustible como aceite, ¿no? Para el calentamiento. Eventualmente va a haber un delta T modificado en donde la diferencia entre el punto más caliente que fue entregado al proceso del punto pinch. Y terminamos con un ejercicio. Nos dice the problem table cascade for the process in figure 16.2 is given in figure 1618. Using the grand composite curve, for the two levels of steam at saturation conditions and temperatures of 240 and 180 degrees Celsius, determine the heat loads of the two steam levels and maximizes the use of the lower pressure steam. La parte A. La parte B, instead of using steam, a hot oil circuit is to be used with a supply temperature of 280 and a CP of 2.1 kilojoules kilogram Kelvin. Calculate the minimum flow rate, that is mass flow rate of hot oil. Okay. Entonces, aquí nos hace el ejemplo, estamos en el libro de Smith, el capítulo 16, si estoy correcto, sí, 16 del libro de Smith. Y en este ejercicio nos hace referencia una vez más a la figura 16.2, ese PFD sencillo de 4 líneas de proceso que habíamos visto al principio. Y nos hace referencia a la tabla de diagrama de cascada que equivale a ese proceso. Y nos dice, para los dos niveles, las dos condiciones o los dos niveles de vapor saturado, recuerde que hace unos minutos vimos vapor de baja presión y de alta presión. Para esos dos niveles, que representan 240 y 180 grados centígrados respectivamente, nos dice, determine la carga de calor, se determine Q en estos dos niveles para que maximizan el uso de vapor de baja presión. Muy bien, este es el diagrama 16.2, que ya lo habíamos visto y ustedes están familiarizados con esto. Este es el diagrama de cascada que ya lo habíamos visto con ustedes y que se determinó que QH mínimo era 7.5 y QC mínimo es 10. Con esa información procedemos a hacer pues lo siguiente. Como en la primera parte no tenemos que determinar la carga de calor para 240 y 180. Recuerde que este calor sobre el punto pinch está cayendo en cascada. Entonces, tenemos que tomar estas cantidades menos delta T mínimo dividido para 2. Entonces, en este proceso, recuerde que el delta T mínimo fue de 10 grados. Delta T mínimo dividido para 2 es 5. Sería 5 menos 240 y 5 menos 180. Estamos hablando de 175. 175 se puede interpolar en este rango, en este intervalo que nos da un delta H de 4. Eso es justamente lo que ocurre. Y esto viene a ser para la parte de baja presión, el equivalente a 175 en temperatura modificada. ¿Por qué se le baja la delta T mínimo dividido para 2 menos la temperatura del vapor? Porque está cayendo en cascada, está actuando como una línea caliente que está entregando calor, está cayendo en cascada el calor, como es el flujo natural de la parte de la línea de mayor temperatura a la línea de menor temperatura. Y como está actuando así, cayendo el calor en cascada de la línea de baja presión particularmente, se le hace pues el delta T mínimo dividido para 2 menos la temperatura real, ¿no? De 180. Y ahí se observa la interpolación, 175 menos 145, que es en este rango, dividido para 185 menos 145 por 4. Esos 4 megavatios vinieron de aquí y se obtiene pues un resultado de 3 megavatios. Entonces 3 megavatios se obtuvo en la línea de baja presión, se puede decir entre comillas baja presión. Y obtuvimos de este gráfico de cascada que el QH mínimo, o sea, el input que hubo de vapor saturado, que proveyó el calor mínimo requerido en la forma de vapor saturado fue 7,5 megawatts. No puede haber una cantidad mayor a esta. Entonces los 240 que nos dieron aquí, que representan 235, 240, claro, 235 va a estar aquí, en este intervalo. Pero a la vez sabemos que ya se determinó cuál fue la carga de calor para la línea de baja presión, que fueron 3. Por lo tanto, la diferencia con el calor que se ingresó al proceso debe de ser la línea, el rango de calor de la línea de alta presión, que es justamente lo que se observa aquí. 7,5 fue lo que se puso en el proceso. Más allá de eso no fue, porque uno trata de ingresar lo mínimo necesario, porque el vapor vivo cuesta. Cuesta porque se tiene que quemar galón de combustible búnker o pie cúbico por minuto de gas natural. Eso cuesta. Entonces se ingresa la cantidad de vapor necesaria, pero no en exceso, ¿no? Entonces el calor necesario fue, según lo expresado, 7,5 y se determinó que 3 era el calor de la línea de baja presión. Entonces la diferencia es 4,5 como se observa aquí en esta línea. Lo graficamos, la línea de baja presión, pues el 3 representa este punto aquí y el 7,5 según el diagrama de cascada representa este punto, de tal manera que la diferencia son los 4,5. Muy bien, en la parte B, y con eso terminamos, en la figura 1626B, que es esta figura de acá, shows a grand composite curve with hot oil providing the hot utility requirement. If the minimum flow rate is required, then this corresponds to the steepest slope and the minimum return temperature. Entonces, para determinar el flujo de calor, recuerden que, claro, el flujo de calor. Entonces, va a tomar en cuenta la temperatura más alta que alcanzó este proceso, que equivale pues a este delta H, la temperatura más alta. 275, que fueron 280. ¿De dónde salió eso 280? Bueno, eso salió de aquí, la parte B. Si utilizamos un circuito de aceite caliente en lugar de vapor, una temperatura que se provee, una temperatura de 280 grados centígrados con ese equivalente SP, calcule el flujo mínimo, flujo másico mínimo de aceite caliente con estas condiciones. Entonces, con eso en mente, tenemos 280 y como está cayendo el calor en cascada, menos delta T mínimo dividido para 275, el punto pincho está en 145, ese diferencial son como 130 y claro, sabemos que lo máximo, según la tabla de cascada, de calor que se ingresó al sistema, el QH, eso fue lo máximo, QH mínimo por 7,5 megavatios. Pues este diferencial se va a tomar en cuenta en esta fórmula que ya fue utilizada para nosotros, MSP delta T, despejando para M porque nos están pidiendo el flujo másico de aceite caliente, es Q dividido para CP delta T. Y Q viene a ser 7,5 megavatios o 7,500 kilovatios o 7,500 kilojoules por segundo, dividido para 2,1 kilogramos centígrados, que nos dio el problema, y el diferencial de temperatura. Que dicho sea de paso, aquí son 130 y aquí en temperatura modificada también son 130, 4 y 3, 7, siguen siendo 130, o sea, ya sea que haga la operación en temperatura modificada o en temperatura real, le va a dar el mismo delta T. Y obtuvo un flujo másico de 27,5 kilojoules por segundo. Esto de jóvenes, solo me pasé felizmente 2 minutos y eso es por esta semana. Espero, Dios mediante, no se olviden el día viernes entregar la tarea. Van a tener la tarea 4 respecto a este tema y esperamos terminar este tema el día martes próximo. Y luego, una vez más, empezar con el tema de reactores. Digamos, empezar con el tema de reactores para ustedes. Eso de jóvenes, gracias por su tiempo, gracias por su paciencia y que tengan un excelente fin de semana. Nos vemos, Dios mediante, el próximo martes. Y que la pasen muy bien, jóvenes. Muchas gracias.
Gracias, profe.
Sí, la tarea es para el día viernes. La tarea 3 está para el día viernes. Creo que está especificada. Lo voy a revisar, pero está especificada para el día viernes en la noche, por favor.
Muchas gracias, profesor.
Gracias, profe.
Gracias. Una muy buena noche con todos.